So in this 28th lecture, the topic that I'll discuss today is conductivity. This article will discuss conductivity for conductors as well as for semiconductors, for intrinsic as well as extrinsic semiconductor. So before I come to this topic conductivity, what I have discussed already with you is that in general, you know that if you have a conductor, I'll start with a conductor first. Suppose you have a conductor here. There's a conductor of length L, and suppose the cross-sectional area of this A is A, then the resistance R is given by rho L by A, and this rho is called the resistivity, and this resistivity is Ra upon L, and the conductivity is the reciprocal of this 1 upon rho, reciprocal of this resistivity, and is equal to L upon Ra. At the same time, I told you that if I apply an electric field here, if I apply a voltage V here, the electrons in this will drift with a particular velocity, and that velocity is known as drift velocity. I discussed with you Vd, which is given by mu into E. Applied electric field is E. This Vd is equal to mu E, where mu is called the mobility. So keeping all these things in mind, I'll discuss this conductivity with you, and conductivity is represented by sigma, which is equal to L upon Ra, that we have done. But now we'll discuss the conductivity in terms of this mobility. So what is the conductivity in terms of mobility? So let's come to this point. Conductivity, initially I'll discuss with for a conductor. Suppose I say that I have a conductor here. Let's take that there's a conductor here. It's a conductor. Suppose you have this conductor here, and I say that the length of this conductor is L, and if I say that the cross-sectional area of this conductor is A, I'm not writing the language here, that consider a conductor of length L and cross-sectional area A, and if I apply an electric field here, if I apply an electric field means if I apply a battery of voltage V, it is very clear that the applied electric field E is equal to V by L. Now, on the application of this electric field, the electrons will drift. These electrons will drift with a particular velocity, that is called drift velocity, and because of this drift velocity, a current I will flow in this. I say capital I. A current I will flow in this circuit. I hope that this point is clear to you. Now suppose I assume that let us say that n, small n is the electron concentration, I say it is the number of electrons per unit volume. In unit volume, the number of electrons are n, and suppose I say that E, small e, is the charge on one electron, is charge of an electron, of one electron, and you know the value of this E is 1.6 into 10 to the power minus 19 coulomb. So if E is the electronic charge, I can say. So therefore, if you see that what will be the number of charges or number of electrons crossing per unit volume. So from here I can say, therefore, the number of electrons passing or crossing, okay, I'll say crossing unit volume. Now in unit volume, the number of electrons are 1, or I can say number of charge, I can say, not number of electrons, I will say number of charge flowing through, or let's take a different one. I can say that the charge flowing, let's take it this way, charge flowing, or I can say crossing, one are the same thing, charge flowing or charge crossing through unit volume. What is the charge flowing through unit volume? In unit volume, the number of electrons are 1 and the charge on one electron is E. So the total charge flowing through unit volume will, of course, it will be equal to N into E. Suppose I take a unit volume here, simply a unit volume, a small unit volume here. So the charge crossing through this unit volume will be N into E, because the number of electrons in unit volume is N. So it is equal to this much. Therefore, I can say that the charge flowing, crossing through this conductor, through conductor means for unit volume it is N into E, and the volume of this conductor, it means the charge flowing through the volume of L into A. That is, I can say it is equal to N into E into L into A. Charge flowing through unit volume is N into E, and charge flowing through this much volume will be this into this. Simple unitary method, charge flowing this unit is this much, then charge flowing through this volume is equal to multiplied by this volume. Therefore, I can say that the current flowing through conductor, suppose I say it is Q. So therefore, current flowing through this conductor. I know that the current flowing through this conductor is I, suppose, and as per definition of the current, I is equal to Q by T. This I is rate of flow of charge. So I can say that this I is equal to, this implies that value of this current, and of course this current is nothing, this is the current which is due to the drift of this electrons, and it is the drift current. So this I is equal to N into E into A into L, same thing, divide by time. So I write this T here, L upon T. Now look at this. Now I can say that this current I is equal to, this I is equal to NEA. This L is the length of the conductor and T is the time in which it crosses this conductor, and the distance L is this distance upon time is velocity, and electrons are moving with drift velocity. So I can say that this L upon T is nothing, it is the drift velocity. So I can say that this I is equal to N into E into A into Vd, where Vd is the drift velocity. Why? Because I am saying that this L upon T, I am writing here, this L upon T, it is nothing, this is the drift velocity Vd. This implies that I can say that the value of this I, drift current, of course this current is nothing, it is the drift current, and this current is equal to drift current N into E into A into Vd. We have discussed that this Vd is equal to mu into E. I told you that drift velocity, this Vd is equal to mu into E. So I have applied the value of Vd is equal to mu into E, and therefore I can say that this I is equal to N into E into A into mu and electric field, E is the applied electric field, which is equal to the voltage per unit length. It is the potential gradient. So I apply the value of E is equal to V by L. All I have done is I have applied this is equal to V by L. Now if you see one more thing, that this I can write this I as V by R, or I can say that this is equal to I is equal to V upon R. Remember that this capital V is the applied voltage and small vd is the drift velocity. V upon R is equal to N into E into A excuse me, V by L here. I cancel this V, and from you can say I just do the cross multiplication, L upon RA. This implies that this L upon RA is equal to mu into N into E, mu into N into E, and this L upon RA is nothing, this L upon RA is the conductivity. Therefore I can say this implies that the conductivity of a conductor is equal to mu into N into E. And a very important relation this is. The conductivity of a conductor in terms of mobility is equal to mu, where mu is the mobility of electron for the time being. I say that in general is the mobility of the charge. So mu into N into E. N is the number of charge per unit volume and E is the charge on one particular this thing, whatever particle you have, charge particle. Here you have electron. Now I'll generalize this for semiconductor and for semiconductor intrinsic as well as extrinsic semiconductor. So what we have derived that sigma is equal to mu N E, and this is in general, this is not only this much, it is for a conductor. I can say this sigma for a conductor. So now let's generalize it for a semiconductor as well as for intrinsic semiconductor as well as for the extrinsic semiconductor. So let's see what is the conductivity of semiconductor. Conductivity of conductor we have seen. Let's discuss the conductivity of semiconductor. I represent this by sigma, and in suffix I write this as SC. SC means in general for a semiconductor. Now in case of semiconductor, as I told you that you have electron as well as hole, so the contribution of current is due to electron current as well as the hole current. So conductivity due to electrons and the conductivity due to holes. So I can say that in this case conductivity of a semiconductor is equal to, I can say conductivity due to electrons. I represent this N, conductivity due to electrons, plus the conductivity due to holes. I represent this by P. That is, this is the conductivity due to electrons, N, and P holes. Conductivity due to this much. Now we have just derived that this conductivity is equal to mu into N into E. So I can say that the conductivity in general of a semiconductor is equal to mu N E. So I can say it is mu N into E. I'll just tell you what all these things are. And for this plus mu P into P into E, where I have discussed this this N, where this N is electron concentration. Electron concentration, that is the number of electrons per unit volume. This P, similarly this P is nothing, it is a hole concentration, that is the number of holes per unit volume. Mu N is mobility of electron. Mu N is mobility of electron, and similarly this mu P, this term mu P is the mobility of hole. Is mobility of hole. For conductor we derive that is equal to mu Ne. Now for semiconductor it is due to electrons and due to holes. So this is the conductivity due to electrons, mu Ne, and this is again mu Ne in spite of writing N as the number of electrons per unit volume, it is the number of holes per unit volume. So it is equal to this much. So I can say that the conductivity of a semiconductor is equal to, I take this E common from here, it is equal to n mu n plus p mu p, this factor, into the electronic charge E, which is equal to 1.6 into 10 to the power minus 19. So in general, this is the conductivity of a semiconductor in general. Let's come to the, now when I say semiconductor are of two types, intrinsic and extrinsic semiconductor. So let's discuss next. This is the first heading. Second, I'll discuss the conductivity of intrinsic semiconductor first. So conductivity of intrinsic semiconductor, that is pure semiconductor of intrinsic, SC means semiconductor, and I represent this by sigma. In suffix I write this as SC. Now since I have just derived that you have conductivity of semiconductor in general, conductivity, I call this as equation A. For example, I am rewriting this equation A. Conductivity of semiconductor, we have just derived that this is equal to n mu n plus p mu p into E, this factor into E. Now since in intrinsic semiconductor, I told you, in intrinsic semiconductor, the electron concentration is equal to the hole concentration, and it is given by the intrinsic concentration Ni. I have discussed this in the last lecture with you. So this is equal to N, this is equal to P, these two are same, and it is equal to Ni. So I substitute this here. So I can say that the conductivity of intrinsic semiconductor, will be equal to N. I take this Ni common. This is also equal to Ni, this is also equal to Ni, common Ni. So mu N plus mu P into the electronic charge E. This is the conductivity of intrinsic semiconductor. Now let's come to the conductivity of extrinsic semiconductor. And for extrinsic semiconductor, again it can be conductivity of N type semiconductor or the conductivity of P type semiconductor. So for extrinsic, I'll consider for N type semiconductor. So what is the conductivity of N type semiconductor? Let's discuss this. Next is, I'll consider conductivity of N type semiconductor, and I represent this term N type's conductivity of course by sigma, and here I write as N type in suffix. That's all. Conductivity of N type semiconductor. Now again, since I have just derived that in general conductivity of a semiconductor is equal to, in general for any semiconductor, is equal to n mu n plus p mu p into E. So since this is equal to n mu n plus p mu p into E. Now let's come to N type semiconductor. I told you that N type semiconductor, let's recall this. I told you that you have an intrinsic semiconductor. You add a donor impurity Nd, and the resulting semiconductor is N type semiconductor. And in N type semiconductor, I told you electrons are far greater than the number of holes, and these holes are approximately equal to the donor concentration. This thing we have discussed already in the last lecture. So since I can say this equation A, I rewrite this. Since in N type semiconductor, in n-type semiconductor, you have number of electrons are far greater than the number of holes, or these are the majority carriers and these are the minority carriers. So I neglect these holes. So I can say that the conductivity of n-type is approximately equal to, I am neglecting this. It's not that this does not, I am neglecting this. It does not mean that this does not exist, but it is very less as compared to the electrons. So that's why I'm saying it is an approximation. It is equal to n into mu n into E. I neglect this. And also I know that since the number of electrons per unit volume is approximately equal to the donor concentration, that is the amount of the impurity per unit volume that we have added. So I can say that the conductivity of n-type, is approximately equal to, this n is approximately equal to nd into mobility of electrons into charge of electron. So I hope that this is clear to you. Then the last topic, or the last heading I can say, is the conductivity of p-type. Conductivity of p-type semiconductor, and I abbreviate this as, of course, sigma for conductivity, and in suffix I write this as p-type. Now again, I know that conductivity of, in general, the conductivity of any semiconductor is equal to n mu n plus P mu P, irrespective of this whether it is intrinsic or extrinsic, P mu P into E. All these things are approximated from this particular relation only. Now since in p-type in p-type semiconductor, holes are majority, charge carriers are far greater in number as compared to the electrons, so I neglect this. So I can say that the conductivity of p-type is approximation. I neglect these electrons, they are less in number. It is P mu P into E, or since these holes are approximately equal to the acceptor concentration Na, that is the number of acceptor atoms by which it is doped per unit volume. So I can say that the conductivity of p-type material is approximately equal to Na into mobility of holes, and of course charge of electron and hole is same. So I can write that this is the conductivity of a p-type semiconductor. So this is the relationship between the conductivity and mobility in case of conductors as well as in case of semiconductors. Then again, for semiconductor, whether you talk about the intrinsic semiconductor or extrinsic, in extrinsic whether n-type or p-type semiconductor. So I'll stop it here today. In the next lecture I'll deal with some numericals based on this.